Okay, and in this section we want to talk about solving trigonometric equations. Now what makes something a trig equation? First of all, it's an equation. You have a trig function in it, but you're taking the trig function of the variable, like sine of x. So if you had, x squared plus sine pi over 7 equals 4, that's not a trig equation because the sine of pi over 7 is a constant, okay? So the variable's not in the angle there. Okay, so and note in this section, when solving equations, the answers are given in radians. You could do all these problems in degrees as well, but again, we're preparing you for calculus where everything is done in radians. Okay, let's look at the first example. It says, solve the equation 2 sine x plus root 3 equals 0 over the interval 0 to 2 pi. Okay, so we're looking for solutions to this equation, but the values of x, the angles, are all between 0 and 2 pi. Right? So what's the short-term goal with solving a trig equation? Typically you're trying to work it down to trig function equals trig function, or trig function equals a number. And I think almost all of these are trig function equals a number. Okay, so we want to isolate the trig function. So if we subtract root 3 from both sides, and then divide both sides by 2, you get sine of x is negative square root of 3 over 2. So I have trig function equals a number. Okay, now it's just a matter of finding all the values of x from 0 to 2 pi that satisfy that equation. Well, sine is negative here, so let me draw a picture. In which quadrants is sine negative? Sine is negative in the third and the fourth. So I have an answer in the third and an answer in the fourth. And sine, use the fraction here to label your side. So sine is opposite over hypotenuse. Opposite over hypotenuse. Now you should recognize these numbers. These are 2 of the 3 numbers in one of our special triangles. The other side is 1 and negative 1. And notice, because these triangles are congruent, even though I didn't draw them that way, the reference angles are the same. Now this is obviously our 30, 60, 90 triangle. And notice this angle is opposite the long leg, right? The short side is 1. That's your 30 degrees. This is your 60 degrees, 4 pi over 3. Same thing over here. Right, so the new thing is just working down to here. Once you get down to here, it's doing stuff we did before, right? Sine is negative in the third and the fourth. Use these 2 numbers to put 2 sides on the triangle. We recognize the third side here because of the special triangle. We recognize the reference angle, and now what's the solution for x? Now remember, we're measuring from standard position, so one solution, the answer is not pi over 3. You go from here to here. So that's pi plus pi over 3, which is 4 pi over 3. There's one solution. And then the other solution, standard position, you go from here all the way around to here. Notice that's 2 pi, all the way around is 2 pi, back up pi over 3, and 2 pi minus pi over 3 is 5 pi over 3. So there's your 2 solutions. Okay? So use your numbers to draw your triangles, find the reference angles, and then use your reference angles to find the angles in standard position. Okay, the next example, same sort of question. The equation is cosine squared x plus 2 cosine x plus 1 equals 0. Again, find all the solutions on the interval 0 to 2 pi. Now notice on the first example, we just had one trig function by itself, sine x. Here we have a cosine x here and a cosine x here, but notice if you think of cosine, replace cosine x here with, say, q. This would be q squared plus 2q plus 1 is 0. That's a quadratic. Okay, and how do you solve a quadratic equation? One way is by factoring. So this is called a quadratic equation in cosine x. Like I said, if you replace cosine x with q, it becomes a quadratic. So let me try to factor this. Well, cosine squared, you have cosine x and cosine x. And 1 is just 1 and 1, and because it's plus and plus, the only possible way that could factor is cosine x plus 1, cosine x plus 1. But always check your factoring by remultiplying. Cosine squared, cosine x plus cosine x is 2 cosine x plus 1. Okay, it works. So we have something times something is 0, so either the first factor is 0, or the second factor is 0, but they're the same thing, so I don't need to write the other one. Okay? Now, if this were something different than this one, I'd have to write, or that is equal to 0 as well. Well, let's get trig function equals a number. Cosine x is negative 1. Subtract 1 from both sides. Okay? Now I have trig function equals a number. Now, don't write this down. But if you try to argue like I did here, okay, don't write this because I'm going to erase it, right? If I try to do the same thing I did here, right? Where is cosine negative? Cosine is negative in the second and the third, so you would, oh, let's draw the triangles, and think of that as being over 1. Okay, if you only have a single number, just put it over 1 to make a fraction. And then you say, oh, cosine's adjacent over hypotenuse. Now what's the problem? The adjacent side and the hypotenuse cannot be the same thing. That doesn't make any sense. Now that doesn't mean there's no solution to this equation. What this tells me is I'm drawing the wrong picture, okay? This picture makes no sense. Right? So what picture do we need? Well, we've only been drawing 2 pictures in the class, either drawing triangle pictures or the unit circle for quadrantals. This turns out to be a quadrantal. Now you may have recognized that without drawing the picture, because remember when we were graphing cosine, where did cosine hit the highs, the middles, and the lows, at the quadrantals? And notice -1 is where the low is on the cosine graph. So you could have recognized this is going to be a quadrantal from that. So again, I'm using the unit circle here. That's the point 1, 0, 0, 1, minus 1, 0, 0, minus 1. And remember, when you use your unit circle, the x value is the cosine. Okay, so in the first revolution from 0 to 2 pi, where is the x coordinate? -1. Here, that's the only one. So where does that happen? X equals pi. Okay, so there's only one solution here in the interval 0 to 2 pi. Okay, the next one says, solve, again on the interval 0 to 2 pi, solve the equation 2 sine squared x is 2 plus cosine x. Okay, so if you try to do it like this one, let's put everything on one side. You get 2 sine squared x minus cosine x minus 2 is 0. Okay, so I subtracted put everything on one side. So I subtracted 2 from both sides and cosine x from both sides. Now what's the problem here? Well, here we had a single sine x, so we didn't try to factor. Here, everything involved cosine. Here we have a sine squared and a cosine, so you're not going to be able to factor like we did here. Because, yeah, you could have a 2 sine x and a sine x when you factor that, but how are you going to, when you FOIL it out, how are you going to get a cosine out of that? You're not. So what's the game here? We want to rewrite this equation just in terms of one trig function. And we've done this before with the identities, is we can rewrite sine squared in terms of cosine by our Pythagorean identity. So replace sine squared with 1 minus cosine squared. Right? So I've replaced sine squared x with 1 minus cosine squared x. That's coming from the Pythagorean identity. Okay, so if I simplify, I get 2 minus 2 cosine squared x minus cosine x minus 2 is 0. And notice the 2's subtract out. You have 2 minus 2, that's 0. And now we can actually factor this. Remember, the first step in factoring is to pull out the factor out the greatest common factor. Both of these have a cosine x. Since they both have a negative coefficient, I'm going to factor out the negative as well. So negative cosine x times what? So I have a 2 cosine x plus 1. Let me check by multiplying. So negative 2 cosine x times negative cosine x is negative 2 cosine squared x. That's correct. And then 1 times negative cosine x is negative cosine x. So we're good. Okay, so either the first factor is 0. I can ignore the -1. So either cosine x is 0 or 2 cosine x plus 1 is 0. And if you solve this part for cosine, you get cosine x is -1/2. Okay. So notice I worked that original equation down to trig function equals numbers. Let me write them over here. So cosine x is 0 or cosine x is -1/2. Okay. So for the first equation, cosine x equals 0, well, you should know there's not going to be a triangle picture that makes sense there, because you can't have a side equaling 0. That's a dead giveaway. It's a quadrantal angle. So let me come back to my unit circle picture here. So if cosine is 0, I'm interested where is x equal to 0. That happens here, right? And it happens here. Now from standard position, where is that? From here to here, that's 90 degrees. That's pi over 2. So x is pi over 2. And then it also happens here. There's where x is 0, and that's 3 pi over 2. Okay? So here's a combo problem, right? The first solutions are coming because x is a quadrantal, cosine x is 0. And then this is going to be from our triangle picture. It's not going to be a quadrantal. So let's draw triangle pictures for this one. Now where is cosine negative? Cosine is negative in the second and the third. And cosine is adjacent over hypotenuse, so this is adjacent minus 1 and hypotenuse 2, adjacent minus 1, hypotenuse 2. And again, we recognize those are numbers in a special triangle. I have a 1, 2, the other side square root of 3. And this one's negative. Okay, now which triangle is this? It's our 30, 60, 90 triangle, right? 1 is the shortest side, so the 30 degrees is here and the 30 degrees is here. So our reference angle here is 60 degrees, but we're solving the problem in radians. The 60 degrees is pi over 3. And same thing there, they're both pi over 3. Okay, now we need the angles in standard position. So the answer is not pi over 3, the reference angle is pi over 3. So how do you get the answer, the angle from here to here? That's our answer. Well, all the way, halfway around the circle is to here, that's pi, and you have to back up pi over 3, and then pi minus pi over 3 is 2 pi over 3. And then to get the answer in the third quadrant, you have to do pi plus pi over 3, and that's 4 pi over 3. So there are 4 solutions to this problem. So those two and those two. Okay, let's do another one. Now notice the instructions on this next one are slightly different. And it says solve the equation. So sine squared x minus sine x is 0. Notice it doesn't say on the interval 0 to pi. It just says solve the equation. So they want every solution you can possibly find. Okay? Well, what do you think we should do here? Well, let's factor. Greatest common factor sine x. Sine squared minus sine, right? So either sine of x is 0 or sine of x minus 1 is 0, which means sine of x is 1. Okay. Okay, now here's how we're going to approach this problem. It didn't say find all the solutions just from 0 to 2 pi. It says just find all the solutions in the world. But right, since the period of the sine graph, remember, is 2 pi. So once you find a solution to this, if you add 2 pi to that solution, you'll get another solution. Same thing with this one, okay? So we're using the fact that the period of sine is 2 pi. So any solution that makes this true, sine of something is 0, well, let's think about the sine graph, remember, right? The sine graph does, like that. So here would be a solution, whatever x value this is, because this is my sine graph, sine is 0. If I add 2 pi to that, right, you complete a whole cycle, well, that's also where sine x is 0. So as soon as you find one solution, if you add or subtract 2 pi's from that x value, you're going to have another solution. Same thing for the sine x is 1, right? If sine x is 1, if you add 2 pi to that, you're going to have another solution. So we're going to use the fact here that the period of sine is 2 pi. Right? So let's just find solutions to each of these from 0 to 2 pi, just in one period. Now, both of these are quadrantals, okay? Sine of x is 0, you know it's a quadrantal because no triangle is going to have a side of length 1. And sine of x is 1, it's the same like we did before. On the high values on the sine graph, where sine was equal to 1, those were all quadrantals. All right, so let me do my unit circle. I should just leave it, not erase it. That's 1, 0, 0, 1. Minus 1, 0, 0, minus 1. Okay, so for here, where is sine equal to 0? Well, remember, on the unit circle, sine are the y values. So that happens here, right? Here. That's 0 radians. And it also happens here at pi. I'm going to list them separately here. Now, where is sine equal to 1? Okay, again, where's the y value 1 on the unit circle? Right here. So that's at pi over 2. So those are the 3 solutions to this equation in the first rotation from 0 to 2 pi. But as I mentioned, if 0 is a solution to this, adding or subtracting 2 pi's is also going to be a solution. So what do? How do you indicate that to keep adding or subtracting 2 pi's? We put plus 2 pi n. All right, and so where n is an integer. Remember, the integers are 0, 1, 2, 3, 4, etc., minus 1, minus 2. So for example, if n equals 0, you get 0 plus 2 pi 0, so you're at 0. If n is 1, you have 0 plus 2 pi. Well, that's 2 pi, which is all the way around. If n is 2, it's 0 plus 4 pi, which is 2 times around. So you see, if you're at 0 and you keep adding 2 pi's or subtracting 2 pi's, you're going to be here. All right? Likewise, if you're at pi and you add a 2 pi, you're back there again. Plus 2 pi n, and same thing here, plus 2 pi. Okay, so that's how you do all solutions in the world. For a sine, just find all the solutions in the first rotation, 0 to 2 pi, and then put plus 2 pi in. Now, if we were solving this, say, in degrees, which in calculus you wouldn't, but suppose this were in degrees, what would this answer look like? It'd be 90 degrees plus 360 degrees in, because 360 would be all the way around. So there's all the solutions to that. Now, let me caution you, this is a perfectly fine answer, but these two right here, you can write in a shorthand way. Notice 0 is here, 2 pi n, 2 pi n, 2 pi n. You keep landing here. Notice pi radians is here, plus 2 pi n, plus 2 pi n. You keep landing here. But you could combine these two solutions together. What if I wrote x is 0 plus pi n? Okay, so I'm saying this replaces these two. Because if I'm at 0, and I add a pi to it, it puts me over here. Then add pi to that, you're back over here. Then add pi to that, you're back over here. So keep in mind that you may write a solution like this. You may look in the back of the book and just be, well, this one you can't do that with. That would just be the same. But these two you can combine into this form. Okay, you can do this if your solutions are, make a straight line. They're opposite each other. So 0 is here, radians, pi radians is here, and notice together they make a straight line. You can combine them in this way. So 0 plus 2 pi n, you keep 0, add a 2 pi, add a 2 pi, you keep going here. Pi plus 2 pi plus 2 pi, you keep landing here. But notice what you're doing here is you're at 0 and you're going halfway, pi. Then add a pi, then add a pi, then add a pi. So you're getting both of them simultaneously. So just be aware of that. If you see a sine or cosine problem like this, and then the back of the book says pi n, they've combined two of those together. That's what they're doing. Okay, let's look at the next example. Next example says tan squared x equals 1. Again, it doesn't say find all solutions from 0 to 2 pi. Right? It just says find all solutions. Well, the logical thing is just take square root of both sides, but remember, if you introduce a square root, you have to take the plus or minus square root. And so what do we have? We have tan of x is 1 or tangent of x is negative 1. So there's two little equations we have to solve here. Okay, well, where's tangent equal to 1? Right? Well, here, the way we're going to approach this is use the fact that the period of tangent is pi. Okay, the period of tangent of x is pi. So, unlike sine and cosine, I found all the solutions from 0 to 2 pi, but that's because the period for sine and cosine is 2 pi. The period of tan is pi, so all I have to do is find the solutions from 0 to pi. Okay, that's all I have to do. And then we'll have to do a plus something to adjust for all of them. Okay, so from 0 to pi, where is tangent equal to 1? Well, in the second quadrant, tangent is negative, so we're only going to get one solution here from 0 to pi. Okay, so tangent is opposite of adjacent. Now be careful, when sine or cosine are equal to 1, that's a quadrantal. If tangent's equal to 1, this picture makes perfectly good sense. And obviously I know the other side's root 2, it's our special triangle. And notice the reference angle is 45 degrees, pi over 4. Okay, so what are all the solutions from 0 to pi for this? It's x is pi over 4. Right? Now again, the period of tangent is pi. So if I add a pi to this, I get another solution. In other words, down there. Right? Tan is also positive in the third quadrant. okay? So instead of putting plus 2 pi in, I'm using the fact the period of tangent is pi, so I'm putting plus pi in. So pi over 4 is a solution. If I add pi to that, that will be a solution. Add pi to that, that will be a solution, etc. Okay? So I did the 2 pi in before with sine and cosine because the period of sine and cosine was 2 pi. The period of tangent's pi. So once you have one solution, if you add pi to it, you get another one. Now what about tan of x is -1? Again, I don't need to find all the solutions from 0 to 2 pi, right? I just need to find solutions from 0 to pi. Well, tangent is negative, not in the first, but the second. Think of that as being over 1. Tangent is opposite over adjacent. That side is obviously negative in the second quadrant. And I recognize the special triangle, that hypotenuse is root 2. And just like here, the reference angle is pi over 4. Okay, now what's the solution here? Now be careful, the solution here for this part is not pi over 4. You have to get the angle in standard position from there to there. And that angle is pi minus pi over 4. Pi minus pi over 4 is 3 pi over 4. And again, since the period of tangent is pi, if I add pi to this solution, that would give me a solution again over there. And so you put plus pi in. So there's all the solutions for this equation, tan squared x equals 1. Okay? Okay, the next one says cotan squared x minus 6 cotan x plus 5 is 0. And again, it just says solve the equation. It doesn't say just from 0 to 2 pi. Okay, so this is a quadratic equation in cotan x, so I think I'll try to factor. And factors of 5, 5 is prime, so factors of 5 are 5 and 1. Since this is a plus, they're either 5 and 1 are either both positive or both negative, but I have a negative there, so the only thing that could possibly work is that. So let me see if it does work. I have a cotan square, negative cotan x, negative 5x, negative cotan x and negative 5 cotan x is negative 6 cotan x, negative 5 times negative 1 is 5. Okay. So either cotan x minus 5 is 0, or cotan x minus 1 is 0. That gives me cotan x is 5, or cotan x is 1. Okay. Now, the cotan x is 1. We did one like this a while ago. Again, I'm going to use the fact that the period of cotan is pi. So I only have to find solutions to both of them from 0 to pi. Now again, cotan is positive in the first and negative in the second. So the only solution here is in the first quadrant. Think of this as 1 over 1. Cotangent is adjacent over opposite. Again, we know the other side is root 2, and our reference angle is pi over 4. It's your special triangle. So it looks like the only solution from 0 to pi is pi over 4. Okay, that's the only solution there. But remember, the period of cotangent's pi, so if you add pi to that, you'll get a solution here. Remember, cotangent's also positive in the third, so you put your plus pi in. Again, I'm using the fact that the period of cotangent's pi, so find all the solutions from 0 to pi, and then put plus pi in. So that takes care of that one. Now what about this one? If you think of this as 5 over 1, same argument, right? All the solutions from 0 to pi, cotan's positive in the first, negative in the second. So this is a solution in the first quadrant. And cotan's adjacent over opposite. Now what's the problem here? This is not a special triangle. Okay, so I can't say, oh, well, you can figure out the hypotenuse with Pythagorean theorem, but then I don't know the reference angle. Okay, I don't know the reference angle because it's not a special triangle. So here we're going to have to use the calculator. So if I call this, x, right? Cotan x is 5. Now what's x going to be? You're going to have to take cotan inverse of 5 using the calculator. Okay. Now typically in the instructions, I would give the exact value, right? So this. But on this problem, you can't say give the exact value. I mean, cotan inverse of 5 is exact, doesn't tell you very much, okay? So here they want you to use your calculator. Let me get mine. Oh, well, I have the answer here. right? So if we take cotan, first of all, how do we do that? Right, there's no cotan inverse button on the calculator, so let me do some scratch work over here. Cotan x is 5, so that means tan x is 1/5, right? Right, so to figure this out, right, we have to say tan x is 1/5, and so x is tan inverse of 1/5. That's what you have to type in the calculator, right? There's no cotan inverse button. So change your cotan problem to a tan problem and then do tan inverse. And tan inverse of 1/5 turns out to be, again, make sure your calculator's in radian mode, 0.1974. Okay, so again, this one we have to use the calculator because there's no special triangle with sides of length 1 and 5, the legs of length 1 and 5. Okay, so that's the only solution from 0 to pi. So how do we get all solutions? X equals 0.1974 plus pi n, just like we did there. Okay, so the only difference here is we have to use the calculator on that one part. Okay, now the next problem is slightly different. Because the angle that's given is not just x. Okay, the next one says solve the equation cosine 3x is 0 on the interval 0 to 2 pi. Okay, so we're back to just find all the solutions in the first revolution. Okay, notice this is a multiple angle. Okay, so it's not cosine x, it's cosine 3x. Now when they say on the interval 0 to 2 pi, they're referring to x. X is between 0 and 2 pi. Okay, so here's what you do. So if x is between 0 and 2 pi, what is 3x between? Well, if you multiply it all the way through this inequality by 3, you get 0 is less than 3x is less than 6 pi. Okay? So if I want x to be between 0 and 2 pi, 3x needs to be between 0 and 6 pi. So, and I want cosine of this angle to be 0. Now remember, 6 pi is 3 times around, 3 complete revolutions. So what do we need to figure out? We need to figure out, for the angle 3x, where is cosine equal to 0 in 3 revolutions? Right? So this would tell me, what could 3x be? Well, where's cosine equal to 0? Remember, on the unit circle, I know it's a unit circle problem because 0 can't be the side of a triangle. It has to be a unit circle problem. Cosine is the first value. Okay? So 3x could be pi over 2. And where do you hit it again? Down here, that's 3 pi over 2. Now again, 3x has to run up to 6 pi. That's 3 times around. So I've only gone around once. So we hit it again here. Right, now what's the value of that? Notice that's 2 pi and another half pi. That's 5 pi over 2. And then when you come down and hit this again, that's 7 pi over 2. Notice, have I gotten to 6 pi yet? No, I've only gone 2 times around. And then you come up here again, that's 9 pi over 2. And you come down here, that's 11 pi over 2. Right, notice this is 5.5 pi. Right, so I'm still less than 6 pi. But then as soon as I go around, if I try to go up there again, I've gone more than 3 times around, so I'm bigger than 6 pi. Okay, so again, what's my assumption? X has to be between 0 and 2 pi. If you multiply all the way through by 3 in this inequality, you get that 3x, that angle has to, for this to be true, 3x has to be between 0 and 6 pi. 6 pi is 3 times around. So I have to find all the solutions for cosine of an angle is 0 in 3 complete revolutions. Now where's cosine equal to 0 on the unit circle when x is 0? So I get a solution here, that's the pi over 2, and then here, that's a 3 pi over 2, and then back up here again. So that's pi, right, that's 2 pi plus pi over 2, right? And you do this, so every time you hit here or hit here, in 3 times around, you're going to get a solution. Now that's what the angle 3x turns out to be. You may say, wait a minute, 11 pi over 2 is a lot bigger than 2 pi, but that's what 3x is. So if you multiply every one of these solutions by 1/3, that would give me x. 1/3 of 3x is x. 1/3 of pi over 2 is pi over 6. 1/3 of 3 pi over 2 is pi over 2. A third of that is 5 pi over 6. A third of that is 7 pi over 6. A third of that, the 3's cancel, you get 3 pi over 2. And a third of that is 11 pi over 6. So those are your solutions. So notice this is what x is, and because these were from 0 to 6 pi, when you multiply by a third, you get x is between 0 and 2 pi. So those are all the solutions from 0 to 2 pi. Okay? There you go. And I don't think I need this anymore. Okay, now the last example here, it's similar to the previous one because it's not just angle x. It says solve the equation tan of x over 4 minus root 3 is 0. But it doesn't say from 0 to 2 pi, okay? So this is a combo problem of ones we've done. So it's not plain old x, the angle's x over 4, so we have to do something about that. And then it's also all the solutions in the world, okay? Okay, well, obviously we want to get tangent by itself. So tan of x over 4 is root 3. Okay, so again, there's no restriction on x here, right? So when I argued the last one, x is between 0 and 2 pi, so 3x is between 0 and 6 pi. There's no restriction on x here, so let's go back to the things we were doing before when there was no restriction, right? Again, tangent, the period of tangent is pi, so let's find all the solutions to tan of something is root 3 just from 0 to pi. Well, okay, so if I find just all the solutions from 0 to pi, first and second quadrant, tangent's negative in the second, so the answer here, the solution's not going to be in the second for x over 4, right? Tan of an angle over here would be negative, so the only possible solution from 0 to pi would be in the first quadrant, because that's where tangent's positive from 0 to pi. Think of this as root 3 over 1, so tangent is opposite over adjacent. Again, we recognize that's our special triangle, our 1, 2 square root of 3. 1's the smallest side, so the 30 degrees is here, so that's 60 degrees, which is pi over 3. Okay, so the only solution we have, so this angle x over 4 could be pi over 3. But again, we're trying to find all the solutions in the world. There's no restriction on x. So what would you do? X over 4 has to be pi over 3, but the period of tangent is pi, so to get all the solutions, it'd be pi over 3 plus pi n. Okay, that's just like problems we did before, right? So we found all the solutions to tan of something is root 3 from 0 to pi. The only solution was pi over 3 from 0 to pi. But if you add pi, keep adding pi's to pi over 3, you're going to get a solution here, and add a pi, you're here, add a pi, you're here. There's an infinite number of solutions. But now let's just solve for x, right? X over 4 is this, right? I just thought of this as an angle. Tan of an angle is root 3. What are the solutions from 0 to pi? Pi over 3, and then you put the plus pi in to get everything outside of that first quadrant. How do you solve for x? Just multiply all the way through by 4. So x is 4 pi over 3 plus 4 pi n, where n's an integer. Okay? So that one's not so hard. Again, the hard part with these problems is figuring out